Um, Hello. Hello.
Hi.
Hi.
Yes. Yes, Siddharth. Are you talking to me?
Wait. I mean, I think
Your audio is kind of breaking up.
Hi. Sorry. I mean, am I audible now?
I just sent you. Are you back? Okay, so I just sent you. Okay, so here's my preference. I think my preference is to do at the end, that because any such discussion will be open-ended, and I won't be able to cover any material. Okay, the regular material. So if you wish to go and then come back around 4:15 p.m. if you have some work to do, that's okay. Huh?
All right. So I'll come back at 4:15 if that's
Yeah,
if
around
that.
4:15. I think that should be fine. So I expect to start around, yeah. So
All right.
yes,
So I'll
4:15.
just
That should
reconnect
be
at
fine.
4:15
Yes.
if I can. Okay. All right. All right.
Yeah.
Thank
See
you.
you later.
I'll leave now. I'll be back soon.
Yeah.
Okay. At right
Sure.
time.
Yes. Okay.
Okay.
Okay. I might want to start early today. I usually start at 3:35. But the plan for today is to, at the end, around 4:30, 4:15 to 4:30, we will have in a half an hour discussion on project, and Hitat will join as well at that time. So for the first portion, I want to cover congruence closure, as I had indicated last time. I know that we don't have a quorum yet, but I'm going to start anyway because we have things to do. That's okay. Yeah, so I have to start recording. Share screen. So please stick around till the end of the meeting, as we will be having a discussion about project ideas and status of various people as to what their project ideas are. Madhukar and Hitat will be saying a few words about some ideas that they have in case your ideas don't work out. So, stick around. Okay. You've seen this picture quite a few times now. So what I'll be, we've discussed DPLL, not yet DPLLT. And today I'm going to be talking about the basic version of the core solver, which is eventually going to be used to combine theory solvers together so it can verify properties or formulas constructed out of mixed theory. But specifically today, what I'm going to talk about is the congruence closure algorithm for deciding the theory of equality over uninterpreted functions. And this theory is usually called UEF, standing for uninterpreted functions with equality. Okay, I'm going to skip these slides. So these are okay. Yeah, so here is the theory of equality, UF. So usually, as you may recall, that when I introduce the logic, a theory is introduced by introducing first its signature, which is the syntax part of it, and the semantics is either described by giving a bunch of axioms that define the formulas for the theory. And sometimes if it is not axiomatizable, the theory that you're talking about, you could take recourse to model theoretic thing. I mean, like when you're talking about the standard theory of numbers, real or integer, then you usually won't see the axiomatization. Anyway, the theory of equality with function symbols, it has equality and a bunch of function symbols, I mean, some constant functions, a bunch of function symbols and predicates. Okay? And these are the axioms that define the semantics of that theory. So it has the, the first, all of them are defining what equality means over terms constructed from these function symbols, constants, and predicate symbols. So the first three, define the reflexivity, symmetry, and transitivity properties of the equality symbol. Additionally, we have a rule for it's called the congruence rule for assigning meaning to the function symbols and predicate symbols. All it says is that two terms with the same function symbol at the root are equal as per the equal symbol if each of the arguments to the function symbols are equal. And the same goes for predicate symbols. Okay? And that's what is the semantics for the theory. Okay? As a simplification, we just replace, we treat predicates as function symbols with, that maps its arguments to a special symbol, true, okay? And that's it. So I should say that there's also, of course, we assume that this is right now, the negation is there, okay? And it's a conjunctive symbol. When we talk about theory and solvers for theory, it is always going to be a conjunction of atomic formulas and their possibly their negation. Okay, so that's what determines the formulas on this. So any formula, is either an equality over these terms or a negation of those, a conjunction of those equalities and disequalities, that is negation of equalities. That's what determines the thing. Okay? So that's why true, constant true is enough, since yes, so the negation is assumed to be there. Okay. Yeah, so the models of these things are any structures that have a set and an interpretation for the equality that satisfy the axioms of T equal. So on the side here, I have, I show you a domain, okay, for U, which has just two elements, okay, a cloud and the sun. So, and I ask you, I pose the question, if the first interpretation for equality, I1, okay, which defines what equality is, which gives an interpretation of equality as a binary relation. If that is a model, so UI1, if it is a model, I just now define what a model is. A model is anything that satisfies all the axioms that I've listed here. I don't have any function symbols that map things. These are just some constant symbols. Is the interpretation of equality given by I1
it can't be a model, right? Because reflexivity is not included in I1.
Correct. So, I mean, not only, yes, reflexivity, I mean, it just says commutativity. Reflexivity is not there. Yeah. So, and you could say that not even the, as a result of that, transitivity is also not there, correct? Because if, transitivity says if x equal to y and y is equal to z, then x must be equal to z. So, which means that this will require star to be equal to star, right? How about the second one? That's correct. So I1, the interpretation one, is not a model. Okay, so how about I2?
Yeah, it will always be a model no matter what interpretation of functions we
Correct.
take.
So the rest of you following that, okay? Why I1 is not a model? Yes.
Sir, why I1 is not a model?
Yeah. My question is if you understand why I1 is not a model. Kapil,
No, sir.
you do not understand why it's not a model.
Yes.
Okay. So let's take see if so. As I said, so if this is all that is there in the binary relation associated with equality, so we require that equality should be
Flexibility is not there, right?
is correct. That's
Okay.
that,
Okay.
that
Sorry,
is,
sir, I was thinking something else.
yeah. Okay. So questions is interpretation given by I2 if that's a model.
Yes, it is.
Okay. Yeah, because reflexivity is satisfied. Commutativity is also satisfied. Okay, and no. Yes, and because this is the only thing, so even the transitivity does not generate any more equivalences between the elements in U than this one. So I3.
Yes.
It is also.
Yes, correct. Okay, so that's what. Of course, I have not shown any function symbols in here, so that there's instantiations of the congruence rule is not there. So I don't know if I have examples, but that is what. Okay, here is an example for that. So here is a function, a symbol that is if this is satisfiable. I think we have gone through this example before, but just to make sure that you understand the congruence rule, if this has a single a constant function a and a function symbol f, is this satisfiable? Or more simply, what I have is if f cubed of
No, right.
yeah, because it violates the as per congruence rule, then if you apply f f squared to both sides, then so you will have to have by this fa equals a, correct? Yeah. Yeah. So the congruence closure algorithm is the classic algorithm that can be used to decide these kinds of formulas consisting of a bunch of equalities, a conjunction of equalities and inequalities over functional terms over a set of finite functions. Okay, so here is the algorithm in a kind of over an example, giving an intuition, informally describing it. So first you place each subterm that appears in the formula into its own congruence class, okay, into its own set. So here the terms are f cubed a f to the 5, yeah, a and fa. So those are the terms, okay. Yeah, I mean the terms that you could construct out of these things. So you have f cubed, f squared, and as well, okay. Then for each equality, positive literal equality in the original formula. Yeah, see the reason you have f cubed, f squared, fa, they're all subterm of yeah, f to the 4, f squared, etc. are also there because they are subterms, correct, of these of f cubed and f5. So that's why it has. So you only have finitely many terms in the original formula. So every term and its subterms all the way down to the constants symbols are the terms, and they are placed in their own class to start with. Okay, and maybe some of you have seen this algorithm before. Have you guys seen this algorithm before? How many of you, if anybody, has seen this? I mean, the Congress closure computing algorithm. Is there anybody? Or is it completely new? Hello?
No, sir, I haven't.
Okay, so at least some people who haven't. Okay. Yeah, in your data structure class, I don't know if you were introduced to union find algorithm. Okay. You know, as you will see, that is what we will be using as an implementation of this. But since you're not, and you know, so let's go through the things slowly as well. So, and then what you do is for each equality in the original formula, you merge the classes of over, you know, T1 and T2. For every equality, you merge the class of T1 and T2. So, for example, here, f cubed is equal to a appears in the formula. And therefore you merge a and f cubed of a. Okay, so pretty much you're keeping track. This takes care of the equality propagation, you know, over the reflexivity and symmetry, because they are in the same class. Okay, and as you propagate, you will preserve the transitivity rule as well. So you merge the classes for T1 and T2. And then you propagate the resulting congruences. Okay, what does that mean? That you look at all the terms in the original formula, you know, that you know, a function symbol applied to some arguments where you know, two terms in the original formula that might have as one of its arguments one of the elements in the class, and as another argument another element in the same class. Okay, then if applying those two, because since we have made they are equal, so you will be propagating the application of any function symbols that may appear in the original formula to these as arguments. In this case, if I, you know, for example, f4 of a is a term which applies, which you get by applying f to f cubed of a, and a itself is equal, and therefore you get f4 of a will be equal to f of a, right? So that's what propagating congruences means. For every in a pair of elements in a class which you you know, you got as a result of merging this class, you look if there are terms that you get by applying f on either side. Okay? And then you you know, merge those two the classes that contain those two terms. Okay, is that clear? So from here, so propagating congruence means you have to look for all the terms as a result of the equality that you have now propagated. If all the resulting congruences are, you propagate the congruences too. So by merging their classes. Okay. Now this you do repeatedly. Okay. So after this, since you have created merge two classes, you can propagate its own congruences, and that results in F5 of A and F squared of A getting propagated. So you do this, you propagate the congruences until to fixed point, okay, until you cannot propagate anymore, until you're not generating any more congruences, okay? So after this, you don't get any term that are in the original formula, right? Of course, you can keep on propagating by applying function symbols here, but f to the 6 does not occur anymore. And even F4 of A and FA, they're already taken care of, right? So there's no more propagation that is required after this point, as they have you have taken care of all functional terms that appear in the original formula. Okay? This you will have to do for every equality. Okay? Now you take the next equality. So for that equality, the first step will require that you merge the two classes, in which f to the 5 of A and A appears. So it is these two classes. Okay? And then you propagate congruences. Now there are no more congruences, or is there? Okay, I think there is. Okay, because f cubed of A and A now get merged. So F4 of A and F5 of A are new congruences. New congruences means it's just an application of the congruence rule. So this gets merged as well. So that's what. So you can see why this is called a closure, okay? Because it is generating the closure of over equality, okay? Starting from over all the application of all the reflexive, transitive, and commutative rule, and additionally the congruence rule as well. So now you have, once you've propagated all equalities and the congruence, deriving the consequences of congruence rule, then once you've reached the fixed point, then you look at all the inequalities in your original formula. Okay? So if f, the original formula, has a negative literal, T1 not equal to T2, for every inequality you do this. Okay? If with the terms T1 and T2 in the same congruence class, then then the formula is unsat. Otherwise, it is sat. Because the first step derived all the equalities that are generated as a consequence of applying all the rules of equality and congruence, and then you check if the inequality is if they are in the same equivalence class, because the equality infers that, and that contradicts with this thing. Okay. So is it clear? Any questions?
So this is only for terms where the equality expressions are ANDed together.
Correct. It's correct. Yeah. So that is correct, as I observed earlier, and it is worth repeating again. All the theory solvers, the decision procedures for individual theory solvers are all conjunctive. Okay. And you may have special. Okay. So the structure of SMT is the theory solvers usually only operate on conjunction conjunction of the atomic formulas defined by the signature of the theory. And the Boolean combinations of these things are done by DPLLT. Yes. So that's how it is, we do. Now, you could have a decision procedure that also special purpose decision procedure that takes care of something internally, it may allow for the thing, and that could be integrated as well. But at least in the architecture that I'm talking about, I am assuming that all the theory solvers are solvers for conjunctive fragments of formulas derived from that theory. Correct. And you will have to wait till you see DPLLT, how you take care of arbitrary propositional combinations of these things. So in this case, this will be unsat because this one says that F and A have to be not equal, but the other portion is saying that they'll have to be equal. Therefore they are. Okay. So I'll take another example. Fx, yeah, this one. So we start with individual, every term being put in its own class, and then so there's only one equality here, and that equality requires that fx and fy be merged. Now there's no more congruences to generate, because these are the only terms with f as it's at the outermost level. So no more congruence to generate. And so that the first part is done, and therefore now you look at the inequalities. And since x and y are still in distinct equals classes, you say sat. Okay. So that's essentially the algorithm that is used to derive, to check satisfiability of conjunctions over these formulas, which is what UF theory consists of. Any questions?
So for each equality term, we need to propagate. We need to do this propagate the resulting congruences part once for each term, exactly, right? So once we have, say, merged for a particular term, we don't need to propagate its congruences again when we do corresponding merges, right?
No. Every time a class is, two classes are merged, you may get, you may need to propagate. Yeah, I mean, that's why it's done in this order, but this is not the only way in this order, but you have to preserve some order. So here I'm taking each equality, and that results in a single merge. Okay, so every time you merge two classes, there's potentially the congruences could be, you may need to propagate the congruences. Okay.
So not only that congruence, but also congruences from previous merges, or only from the...
I mean, that of course you will have to use, yes. The previous merges, I mean, yes, the previous merges will also play a role in determining the congruence, because the congruence rule says, so here it's all on a single argument. Okay, let's suppose x and y are merged in here. So if there is a term that, yes, your answer to your question is yes, because the previous things may need to be used. But the trigger for that will happen the moment there is a new pair of classes are merged. Okay? So that can happen either when you look at a new equality in the formula. You need to look at each equality in the formula only once if you do it in this order. Okay? So once you do that, there is a merge due to equality propagation. After that, anytime you merge, there can be new congruences that can potentially get generated, which due to this merging, because there are more things being equal, and also, of course, the previous ones. Okay, so especially if there are multiple arguments, okay, of functions. Here I've shown only single argument functions, right? So, but even, yes, okay. So even otherwise, yeah, the old equality might play a role also, yeah. Correct. Yeah. So, but each time you merge a class here, you propagate all the equalities, okay, and then you can move on, okay, so that at each point you will do it until you reach a fixed point, which means that you're not generating any more congruences, and after that you move on to the next equality in the formula. Okay, so each congruence propagation may itself cause two classes to get merged, as we saw, which means that can trigger more congruences being generated. Okay, and every congruence generated means you are merging classes. Yes. Okay. So now a bit of definitions and what exactly formally this means. What does congruence closure computation means? So, these are some, just recap, you guys would have seen this. A binary relation R is an equivalence. It's defined to be an equivalence relation if it is reflexive, symmetric, and transitive, which is what we are trying to propagate. Now, an equivalence relation, which preserves these three rules of equality, reflexivity, symmetricity, and transitivity, is called a congruence relation if it also preserves the congruence rule for every n-ary function. Okay? That is, if for each xi and yi, which appear as arguments to an n-ary function, if they're already in the relation, then so should be the two terms fx bar and fy bar. Okay? So then it is called a congruence relation. As you know, anytime you have an equivalence relation, an equivalence class is defined as it's a set of all elements belonging to a universe that are related by the equivalence relation. Okay, so that set is called an equivalence class. For example, what is the equivalence class of 9 over, say, the set of all natural numbers? This is mod 3. If you were using, the relation that the binary relation is equality under mod 3, what would the equivalence class that 9 is a part of be? What are the elements that the equivalence class that contains 9 contain?
0 mod 3.
Yeah, all mod 3. So 0, everything that is divisible by 3. Huh? Yeah, so that's the idea. So everything that is divisible by 3, you would you would have, because this is divisible by 3. So anyway, so that is clear now what an equivalence class is. And then similarly, you define a congruence class. If R is also, in addition to the equivalence rules, it also obeys the congruence rule. So, and now we are, there's the definition, what exactly a closure is. Okay? So an equivalence closure, RE, of a binary relation is the smallest equivalence relation that contains R. Okay? So for example, so it is the smallest in the sense it contains everything that is equal, starting with R under the equivalence rules of equivalence relation, which is symmetry, transitivity, and reflexivity, and nothing more. That's what it means when someone says it's the smallest equivalence relation. It has to contain everything that is inferred by the rules of equality and nothing more. So for example, what is the equivalence? That is what is called as the equivalence closure, okay? That is, you're generating all equalities inferred by your original binary relation under those rules. So, and this is what the congruence closure algorithm that I informally demonstrated, illustrated, really generates. Okay, that's why it's called the congruence closure algorithm. So what is the, first now we are talking about equivalence closure, and then we'll talk about congruence closure. So what is the equivalence closure of this binary relation, which contains A, B, B, C, and D, D? Okay, really, yeah, what is it?
ABC in one class and D in another.
Yeah, so you just need to keep on propagating all the things. So you should first add all the things that are inferred by the reflexivity rule, okay? Because by the fact that A, B, C, D are elements in the as part of the relation itself, next, and then you propagate, symmetry and everything. So you keep applying those rules until you can't generate any more, okay? And it's important, why I've used the smallest, and it's important for you to understand, because it has to have all the things that are propagated, but no more, okay? And that is why you define it as the smallest equivalence relation that contains the original R itself. So congruence closure RC of a binary relation is similarly the smallest congruence relation, okay? That is the ones that you get all the things that you infer by additionally using the congruence rule. Okay? And the congruence closure algorithm, it really computes the congruence closure or the equality relation over terms, asserted by a conjunctive quantifier-free formula. And that's why this is a decision procedure. It can be used as a decision procedure for deciding equalities over those things. So that's why you see there's no quantifier, okay? So everything is considered as pretty much a constant there, including the zero array function symbols, which are really like variables, but then they are like treated as constants. Okay, so that's what this thing is doing. So is it clear? Okay, so this is pretty much it. Okay, the decision procedure for it, but you need to efficiently implement it. You need especially to propagate these congruences. Okay, so you remember that propagating these congruences, you had to search. Okay, when you merge two things, you need to have an efficient data structure so that these equivalence classes can be represented efficiently, so that you can represent the entire set by a representative belonging to that class, so that it will be efficient for you to merge. And you need a certain data structure to implement congruence propagating the congruences. You need to be able to search your formula for all the terms which have the same function symbol at the topmost level, and then arguments that are in the same equivalence class. So there's a lot of, you need data structure that can efficiently implement these, searching for these things inside equivalence classes. And for that, and that's the thing that I want to share, because once you understand at this level, as an abstract level, this is, one, at one level, but you also need this data structure, since that is interesting. So, the union find data structure, which has application at other places also is a very good kind of data structure to use, and I'm going to illustrate that here now to implement the congruence closure algorithm. So every term here we represent by a DAG, every term in subterms that occur in the original formula. For example, in this case, we have AB, f of AB, and f of AB. And these are just the edges are pointers to the arguments to the function symbol, which is at the root of that term. Okay. So here, this is just a representation of all the terms that appear. In this particular case, every term appears as a subterm of something else, and those are the only things. Now you can have G and then so on. I mean, other things, if they are disjoint, you may have separate things as well. So then, in order to really efficiently check if two elements are in the same equivalence class or not, which is some operation that we'll have to frequently do in order to merge classes in the congruence closure algorithm that you saw. It is useful to maintain, and that is done by maintaining a pointer called a find pointer. Okay? This is nothing new. This is a very classical data structure called union find to any time that you want to merge sets based on certain criteria. So this find pointer is, it points to another node in its congruence class or itself. So for example, so here the blue edges denote the find pointer. So A is, you choose one as a representative of the class here, in this case A, and there should be a self pointer for node 3 as well, but I've not shown that. And yeah, so this indicates the situation that A, f of AB, and f of AB are in the same equivalence class, and that's why these things, every node has a pointer to the representative, the node which is the representative of that class. If that is in a class by itself, then it'll just have a self pointer. Okay, and B in this case is in its own equivalence class, and that's why there is no pointer from any other node to B. Okay. And then you also, in order to be able to propagate congruences, there's an additional piece of information that is maintained in the data structure. This is called congruence closure pointer, okay, CCP. So each representative in the only the representative in for each equivalence class has this field, the CCP field, which stores all parents of all nodes in its congruence class. Okay. I mean, yeah, and the reason is that once you have those, yeah.
How there is a find pointer from 1 to 3?
Why is there a pointer from 1 to 3?
Yes.
Yeah. I'm just showing you the situation in which A, f of AB, and f of AB comma B are all happen to be merged into the same class. Okay, and that's all. Okay, and that, I mean, I'm just to illustrate what find pointer mean. I'm illustrating that. Say, assuming that those three terms are in the same equivalence class, then you would have,
Not corresponding to the formula you have stated there, right?
Yeah, in this case, it so happens though they will be merged also as per the equality, propagation, and congruence closure as well. Okay, because f of AB is equal to A, therefore,
Okay. Yes.
and that's why f of AB can be equal to FA and so on. So as is also equal to FA, correct? Therefore, so they are indeed will end up in the same equivalence class if we're using the congruence closure algorithm. Yep. Okay, coming back to CCP. So here f of AB, f of AB, comma B, they are all in the same equivalence class, and therefore what it says is it has all the parent nodes, each representative. Only the representative in the equivalence class will have this CCP field. Okay, so it stores all the the root of all the parent nodes. So f of AB is a parent node of A, and therefore that is stored. F of AB is also a parent node, I mean, of something in the equivalence class, and therefore it stores both 1 as well as 2. Similarly, B is, although it's in its own equivalence class, it is also part of the terms f of AB and f of AB, okay? And therefore, it also, both are its kind of parents and grandparents, and therefore it stores 1, 2. And you can see why this is mainly used to make the propagations, the search for the terms which you will have to check in order to see if they are equivalent under congruence rule more efficient. Okay, that's why you keep these things. Yeah. Okay. So is that clear? Why, how CCP is, what exactly CCP means? Yeah. Yeah. So this is classical union find data structure, maybe with some variations. So congruence closure algorithm, how to implement the congruence closure. Oh, somebody's here. Yeah, Hitat said he'll be joining it. Yeah. So to begin with, you have, no, so once again, okay. Yeah, this is a situation. So find, as you know, returns the representative of a node's equivalence class by following the find pointers until it finds in a self loop. So, okay, there are two operations. Find is one function, and union is another function. Okay, so this is merges any two equivalence classes by actually chasing the find pointer. So this illustrates the merging of an equivalence class which contains A and f of AB and f of AB. Okay, so that's what it does. Okay, so it chases the two. If I want an I2 or two separate nodes that need to be merged, the terms need to be merged in the class, and then you chase the find pointer to find each of its representatives in the equivalence class that they belong to, and then you make the other one the same, and then you merge the CCP field of that, and you make the CCP of once you find the representative, you just discard the CCP of F. See, to start with, the F of AB, comma B was in a separate equivalence class, and that's why it had its own CCP. And since it does not have any parent, that was empty. So as a result of this merging, of unioning those two, you will end up creating this a pointer, which is what is done in the second statement. Okay, you make the find to go to the representative of the other class, and you merge the CCP of those two things. And in this case, it remains the same because the CCP for F itself was for node 1 was just empty. So this is the other thing, that the basic method that is used for merging two equivalence classes. So given this data structure and these basic operations, now you are, you're ready to implement the congruence closure algorithm. So that itself is done using two functions. One which checks if two terms are congruent, okay, as per the equality over its arguments. Okay, so congruent function takes as inputs two nodes and returns true if and only if it has the same functions at the root node, and the corresponding arguments are in the same congruence class. Okay. So, for example, if you applied a congruent to 1 and 2, what would be the answer? So you would have one and 2, they have the same function symbols, so the condition 1 is met. And then corresponding arguments, the argument of the term at node 1 is f of AB. And argument of node 2 is A. And since f of A, f of AB and A are in the same equivalence class, and B is equal to B, therefore, so those two are equal. So f of AB B is equal to f of AB. Okay, and that's why so they are equivalent. Okay, so and then you have a merge. Okay, so this is this just checks if two input nodes are equivalent under the congruence rule. Okay. Yeah. Now then you have the merge algorithm. Okay, this is the top level merge that implements the congruence closure. Okay, so it this is what propagates equality as well as the congruence closure using find, union, and the function that we defined before congruent. So to begin with, you have everything will be in its own equivalence class, and that's why you don't see any blue pointers. Okay, and so since each of them is in its own equivalent class, it just has, of course, A will have its CCP as 2 because it's its parent is only F. Okay, and A is the only in the equivalence class. B will have 1 and 2 because it's part of B is part of F of AB as well as F of AB. Okay, so what you do is then so if you want to merge two nodes, you get their representatives, find I1 and find I2. If they're already in the same equivalence class, then you don't have to do anything. If not, you get their two CCP fields. You get the two CCP fields, and that will be used actually to check congruence later on. First, so you store their CCP, get the CCP, and then save them into variables P1 and P2. You merge N1 and N2. So that you do. And after that, so first you merge, okay, for each equality that you do. So, and after that, you will have to check if you search through all the terms, okay, in the thing, and check for each T1 and T2 that that you get as a result of merging, because this has all its parent nodes for each of the elements in the CCP field. If they're not in if they're not in the same equivalence class, but the two terms are congruent, with, if there is some term which is congruent as a result of these two things, then you have to merge. Okay. So this illustration will we have. So you take FAB is equal to A, okay, and you start with that. So what do? So then you you have to merge those two classes. Therefore, that's where you use you do this. So then this merging of N1, N2, it'll create this one, and you will need to look at all the terms, all the parents, okay, in this, you have one is empty, the other one is, 1, 2. So you have to take those two things, and you will check if the, because there is, you check that, you check all the parents, okay? So you look at F. These two are already in the same equivalence class. So you check if two, this F here, which is the parent in the CCP, okay? This is the, before, okay, what you have to do is P1 and P2 are something you have saved before you merge. So you're taking the cross product of 1 and 2, okay? That's what you're taking. As a result of merging, you see P1 and P2 are saved before the merge. Therefore, this P1 cross P2, P1 here is 1, P2 here is 2. So you will be, those are the things that will get merged. And that's why those are the two arguments. So you will, by looking at the parents, you will look at the parent of this, which is 2, and the parent of this is this. So that function, when applied to 1 and 2, if they are equal, okay, that's what congruent checks, because T1 and T2 are equal, and it checks if f of a b comma b is equal to f of a. That's what it is. It is checking that these are the two parents, and therefore it'll then merge that thing. Okay, it will merge T1 and T2 as well, and that's how it is. It's implemented, and this is a recursive function, and therefore you keep doing this until you have generated all of them. Okay, and then finally you have this is the top level algorithm of congruence closure. So where you first construct all the subterms, and then for each Si and Ti in the formula, you will invoke merge, and so you invoke merge, and that propagates both the equality as well as the congruence closure. At the end of reaching the fixed point, then you enumerate all the inequalities belonging to the formula, and you will check for every inequality if the two are in the same equivalence class, which you can check by using the find pointer, then you return unsat, otherwise you return sat. So that's what is illustrated here. So, f of AB, you merge it here. So that was merged, which I've shown in the previous slide, the effect of merge. And after that, you take this and you check if the two they are in the same equivalence class by chasing the find pointers, and you get a violation. Okay, so that's the how union find data structure can be efficiently used to propagate as well as check the propagate equality and congruence, generate congruence closures, and then check the satisfiability. Okay, so that's, and stop here. And any questions?
So when we are unioning two things, we have a choice of which representative we want to take as the representative of the merged class, right? Is there any specific way in which we're making the choice, or is it arbitrary?
Correct, that's a good point. Yeah, so in this case, I think it's arbitrary, although, yeah, because, yeah, I would say it's arbitrary, okay? Very good point, correct. So when you're saying here, when you're merging these two, so why did you choose A's field, right?
Yeah, I mean, it might as well have been 2 as the representative of this class, right? So, I mean, in that first merge.
Yeah, I would think that, that's worth thinking. I have not thought about that. So I think it would be, whether it would be, I think the correctness is preserved by whatever. So what will happen is all of these things will then go to F, no?
Yeah.
How it will be kind of reverse there. But then the root will be, yeah. No, yeah, that's a good point. Yeah. So if the, yeah, I'll think about that. Okay, that's a good question.
I think it will still be correct, but I mean, I'm not sure.
Yeah. Say that again?
I think in this case it will be correct. I don't know if that's a generally.
Yeah, but then what criteria would you use to, in this case, F is in its own thing.
Yeah, I mean, in this case, what will happen is something like one of those 1 or 2 nodes will become the representative of the entire thing. Like everything will point to there.
The point to there, correct. But what I'm concerned is whether the roots, okay, the CCP, that's okay. That's okay because it still has all the,
it will still follow the blue pointers back, so that will be fine, right?
Yeah. The blue pointers will be there, but then it'll 1, 2 will be made as the CCP for F, not for the node 1. That's what you're asking, correct?
Yeah.
Yeah. But if you make that as 1, 2, then that is not exactly the representative, isn't it? Huh? No, but let's look at that. No, it is this one, no? So this is the union, correct?
Yeah, the blue pointers here would point to somewhere else.
Yeah, so if it shows, so find if I1 is n, correct. So if it was like this, this would be empty. So see, but the yes. So if everything is no. Yeah, to begin with, it'll have its own thing, and
Have 1, 2, and that is fine because 1, 2 are the what we would want RCCP to be, right? Even if like the top node is the
yeah, but from here, if what you're asking is if I reverse, if N1 is, I mean, if N1 is node, I mean the class, I mean if you're merging 2 and 1 here, correct? So 2 would go to A, okay, that is fine, 1, 2.
N2.5.
Yeah. Yeah, so the real question is, and I have to work it out to see. Yeah. The only thing that I'm concerned is if when you merge this thing and then you assign it to node 1, say, okay?
Yeah.
If node, yeah, if N1 here is node 1, and here we ended up making that empty, right? So what you're saying is if you reverse this, this will become the thing. So I want to check, I mean, what needs to be checked is if the root pointers will still be adequate, okay? I mean, the CCP field is supposed to represent the roots, no?
Yeah, I think in this example, I think it will be
Okay.
fine.
Yeah. Mm. Yeah, I need to think about that. Okay, so I don't know if why would you think that in general it'll not work?
I don't think. I mean, I'm thinking maybe it'll work in general, but I can only be sure about this example.
Good question. So I'll think about it. And, but, you know, good question, Diganta. Yeah. Okay. So I can't. Rather than since we have some more business, so let's defer that. Okay, and then have get it clarified in the next class. Okay. So yeah. Any other questions? Okay, so let me then hand over to Madhukar. Who's going to go first? Madhukar, you'll go first? Or Hitat, you want to go?
Yes, sir. Yeah.
Huh?
I will go first. Yeah.
Hitat.
Yeah.
Okay, so first, before I'll make both of them co-hosts. So here's the plan for the next 15 minutes or so. You know, how many, I know that we have got some proposals from some of you, and we are reading through it, and then we will be discussing that separately with those that have sent the proposal, okay? And I want to put a firm deadline on when the proposal has to be finalized, okay? And that is next Wednesday. Now that will be finalized either through you make a proposal, we discuss and make modifications, and then that will get finalized that way, or based on some, you know, if you don't have any ideas and you're still, you know, you're not, you need help in getting some assistance and so on, I mean, getting help in deciding, Then you can use some of the general topics that will be discussed today by Madhukar and Vitar. Think about that, and then discuss with us between now and Tuesday. So what I want is by Wednesday, like para half a page proposal as to what you will be doing, and that will be like a draft of a contract, okay, of what your proposal will be. That might either mean that you will have to discuss separately with us if you have your own ideas that needs to be polished, modified, and so on, or you will pick one of the one of the ideas that Madhukar and Hitat will be talking about, and then scope it. Even in that case, there will be some more work that is required from your end, because what Hitat and Madhukar will be giving you is not a fully defined and unambiguous problem statement. Therefore, so that's just an idea. So that's what will happen. So nonetheless, regardless of what path you choose, the final decision and proposal will have to be the proposal has to be finalized by Wednesday. Go ahead.
Yeah. Okay. So yeah. So I'll be like talking about two ideas that I have in mind, which you can take and like you have to modify them, of course, and make them more concrete. Okay. Just give me a minute. Just hide this. Okay. So the first thing is we have signals. So this, for example, this is a kind of a signal, and maybe you can have more like the frequency is like it can vary, right? Because frequency is basically the number of times you see this thing in 1 second or something. So in digital signal, what happens is we don't have this like this is an analog signal, of course, the way I have drawn it, but when you store it digitally, you just take the values at some instance, right? And how many values you take, this is called as sample rate. Okay, so how many values you're taking in 1 second, that is called a sample rate. Now what the idea is that if I give you this problem that, okay, I have given you a signal with some noise in it, and you want to find out the frequency of the signal. Okay, so usually like people use some like FFT or something to find this thing out, but we don't want to use that. And the thing is that we want to use a neural network to find out this frequency. So the sample rate has to be defined, like decided very carefully by you, depending upon what kind of like, it depends on the frequency. So I'll just explain this in 1 minute. So let's say the frequency is, this is like, this is 1 second. So if I take just 2 values in 1 second, then I will never capture this frequency, because I cannot like hope to see this trough, count these troughs if I just take 2 values in 1 second. So this is 1 second, okay? So I have to increase the sample rate, and suppose my sample rate is 10. So I'll take 10 values here, something like that, and then I hope that, okay, I will get these somehow I can reconstruct these troughs, okay, that I can get the frequency out of it if I just sample 10 values in 1 second. So let's say we want to analyze signals with frequency from 10 hertz to, let's say 5k hertz or something like that. Okay, so you want from 10 hertz to 5k hertz. So you have to evaluate what sample rate should be fine for this. It's very easy. You can just take inverse of this or something. But the point is that you will find out a sample rate or fix this frequency such that so you just take a signal and you take, let's say, 1 microsecond of it. So 1 microsecond is 10 to the -6 or something. So you just take that and you evaluate. You just find out what is the number of what are the values that you see in that thing, and that would be the input to a network. So we will have a list as an input which will tell you the value of the signal for the 1 microsecond part, just 1 microsecond. And the task is that we hope to find out the frequency of the signal using this thing. Okay, so you will be given these values, let's say 0.01 or something like that, and you will have values for 1 microsecond, and the number of values would be time into the sample rate, of course. So you have to like find it out. This is very easy things. I will write some description for this when somebody chooses this, if somebody chooses this project. Now the thing would be, you will create a neural network that will find out this frequency for you. You have to make sure the sample rate is small enough that the network doesn't grow too large. So this number should be, I will say maybe around 1000 or 500 or something, like between that would be fine. So you have to find out the sample rate or whatever. Then you will create a neural network which will find out this thing, and this will be your like the network should be very small. So I mean, you only need to use, let's say 3 hidden layer or something with around, let's say 2 to 3 or 2 to 4 neurons in each layer, not more than that, because we don't want it to grow too large, because we want to use Z3 at the end of the day. Okay. Now, when you're done with that, the property that you might want to check are like this. So you have the signal, and maybe you want to find out what is the maximum noise that I can add to inputs such that the output is correct. Okay, and remember the noise is from, like, let's say Gaussian noise and with some mean and some variance, which you can decide on your own. And okay, and then what you do is that, you have to find out more property like this. This is just one example of a property. I didn't think of more property, but this is just one property that I think will be very nice to check, that what is the maximum noise that I can add to it, to a general signal, and my network still predicts my output in a given range, let's say within 1% of the actual correct answer. So that's one thing. So I think this is the idea that I have in mind, and you have for the first idea at first, and you have to find out more properties, of course. Let's say at least 4 properties that you want to verify. You have to verify them and of course write a report and whatever. That's for later. Okay, so if there is any question regarding this, hold on. Like after presenting the second idea, I will take the questions if you have any question regarding this and if you want to take this one. Okay. The second thing is actually much like what we did in the ShapeNet thing. So it would be as follows. So you will draw some shapes, or you will find out from internet, and let's say there will be, you will draw 10 by 10 pictures, or maybe 12 by 12 pixel pictures, and the pictures would be of particular shape. For example, it would be handwritten shape, so it would be like a square, circle, or a square, or something like that. Those images you will like create, and maybe you will also draw, a horizontal line or a vertical line, and they all should be like hand drawn, so that because we want to capture that thing, and maybe slanted line, or so on. And you will like, at least you will have 8 shapes, let's say. Okay, so now you will you might, for getting this data, you can either like just go to internet and just find out whether there is some handwritten shape data or not. You have to search for that. If you don't find it, then what you can do is you can take a sheet and just draw them by yourself, and then find make a program which can split the page, the given image, into shapes. And if your 2 people are in their team, then maybe you can draw like 100 shape each person, and then you can create your training data. After that, what you'll do is you will apply some modification to your images. So for example, you can apply a modification like stretching an image by 10% or in this direction or in this direction, maybe skewing the image like this, or so on, so that this will increase the size of your data, let's say to 1000 or 2000 images. If you apply multiple such transitions, like shifting the images up and down by 10% of the height and so on. In this way, you will like, when you apply all these things in various combinations, you will get a huge data from very small number of images. So that will be your training data, and you will split into testing data or validation data, whatever you have or want. Finally, what you will do is you will create a network that will detect these handwritten shapes. So it's of course a very kind of at least a little bit of practical thing, because you might have shape and you might want to detect what shape the person has drawn. And you can just take the picture, squeeze it to 10 by 10 or 12 by 12, whatever is optimum. You have to find that out, because Z3 at a value where Z3 can handle it. And of course, and also that it is not that small. The resolution is not as small that the figure is just lost, that the shape is lost. You don't want that. Okay, and finally, you also have to use convolution here. So because the reason for that is because convolution is actually will be easier for Z3 to handle, because there are only let's say 9 weights or 16 weights per filter. And if you have 10 filter, then it only amounts to, let's say, 90 weights, which is easier for it to handle rather than having, 15 or 30 neuron in the layers and all. That will increase the number of weights too much, and it will be hard for Z3 to handle that. Okay, so once you have done that, the property that you might verify as like this. So you might verify that given a circle, no matter by what angle you rotate it, it will, if you rotate it by 1 degree or something, it will remain the same. For square and rectangle kind of thing, you can verify that if I rotate it by 90 degree, the output should remain the same. So this all should be symbolic. So you'll say any input, which is a square or a rectangle, if I rotate it by 90 degree, it should remain a square or rectangle. Yeah. Similarly, for horizontal line, you can say if there is an input, which is a horizontal line, then by rotating it 90 degrees, it should become a vertical line. And you can verify such properties, and you can, of course, invent more properties, and at least invent 6 or 7 properties, and you have to verify all of them. Yeah, so these are the 2 ideas that you might take, and you have to make the neural network, and then you have to encode it and whatever in Z3, and then you have to verify these 8 or 7 or 8 properties that you will create and explain. Yeah. So these are 2 ideas that I wanted to present. And now if there's any question about them, then you can ask.
Yeah, one comment that I want to add, Hitat. So yeah. The second thing, Diganta and Saugata.
Yeah.
They would, since you have been talking about some, exploiting symmetry, DNA verification and so on, since you were not yet sure as to what application might be suitable where that kind of exploitation is readily possible. You may want to think about this particular application to see if it suits that.
Yeah, this is giving me various ideas. Both the second one, in fact, even the first one.
Okay. Okay.
I would like to discuss with you at some point, like if you are available after class for 5-10 minutes today.
Yes. Okay. We have one already scheduled.
Okay.
Yeah, but
yeah, whenever it's fine with me.
Yes.
To add to it, one more thing, of course, if you have any question about the first one that I described or the second one, then you can ask. Of course, I think Diganta might take this second thing up, but if anyone else want to have any question about this first one, then you can ask that. Okay, you have to think how to make it more interesting. This is
you have to write up a brief note, Hitat, about this and upload. You had.
So what I was thinking so, but now I think that because I've explained it, I think because it is also the proposal is also an insert has a certain grade. So I think what we can do is that if you have a question, you can ask. Otherwise, if you like this idea, then you can yourself write a good proposal and make a small presentation or something.
So I don't want to overburden it. Yeah, so you can discuss separately, with you if they want more clarification on that. Yeah. So I'm going to insist that you will have to upload. And since this thing, your description and the recording of the thing will also be there. By the way, I forgot to mention one thing, that we have decided to have make for the proposal part 15% of your overall grade assigned for this thing. Did we make 10% or 15%?
10%.
10% of the grade for whatever is a portion for the project. Take your proposal writing seriously.
Yeah, so I think I'll end here. So if nobody has any question, then maybe, you can contact me separately on my WhatsApp or email if you want. And I think Madhukar can start.
Yeah, I think Hitat, you can contact independently. I don't think I need to be there in that meeting. Because especially scheduling all 3 of us will be hard, at least.
Yeah, of course. If you have anything about these 2, then you can just directly contact me and we will schedule a meeting. Yeah, Madhukar, I think you are up.
So I want to ask if, how many of you have, I mean, I know that Diganta, so that you had made some proposal. Kapil, you have, Kapil and your partner, I forget. Kapil,
Yes, sir.
who's your teammate?
Srijato.
Srijita.
He was there. I think he left. He was there.
Oh, you see, we can still discuss. We had I'd like both of you to be there. Okay. So, but in any case, so you have made some proposal. Those are the only. There was a third one. Now, somebody proposed some games. That is you. That is you.
I proposed the game.
But there was something that somebody else proposed.
I think Argit did.
I proposed this afternoon. Yeah.
So you want to stick around?
Yeah.
Yeah. So Sahil and Zubin, you're still here?
Yeah, we had some ideas. Yeah.
Okay. So, but anyway, listen to what Madhukar has to say. One of them. Okay. And I was wondering if you can do, or it's always, yeah. So this is just suggestions. That's all. Go ahead, Madhukar.
Yeah. Yes, I don't know if some of you need to leave early, then you could at least say that you need to leave so that we know who all have not. If for a lecture or for any reason, if you need to leave, because I know that it is already close to 5.
It's getting late. So 5 o'clock, some of you have another class, is it? What do we do? Already almost 5. Okay.
I can stay. I actually want to discuss my idea.
Yeah, sure. But the point is that, yeah, we are, yeah.
So Sahil and Zubin, are you willing to stay?
I can stay, yes.
Is Sahil around?
Yeah, hello.
Yes, Sahil here?
Yeah, I can stick around.
Okay.
Yeah, so if it's getting late and any of you need to leave,
then how do you do? If it's getting late, then we'll have to, one thing you can do is, it seems like you have a very well-organized formal presentation. Do you think that you can upload it and then do it? Or
I'll certainly upload it.
Well, let's do it this way. So why don't you discuss it? Anyway, this thing will be recorded, man. Okay?
Yeah. So I'll discuss it and then upload
There's no obligation for you to stick around, especially if it's since it's getting very late. It's Friday, and you may even have other commitments. Okay, so I don't, I won't insist, but you describe it anyway for whoever is there, and we'll upload it, and then people interested can view it.
Yeah, certainly. Yeah. So I'll talk about a couple of them, and here they are. So the first one is about programs and invariants. So those of you who have known this field of program correctness or program verification, not any great details about this thing, but the logical part of it, at least what we mean by invariants and what we mean by an invariant to be good or bad. So we are going to consider, for example, this is one of the proposals. So you may consider some very simple program, some simple C program like this. Let's say, it has one while loop and one assert, which is immediately after the loop, like in here in the example that you can see. Okay. So this is a very simple example. It has two integers x and y, both are 0 in the beginning, and then for an unknown number of times, you increment both x and y by 1 in a loop. Okay, and you want to assert that y is greater than or equal to 0 when you exit out of the loop. Okay, so now sorry, there is a typo. Yeah, just 1 second. I'll be back.
Yeah, Rishikesh, I just wanted, while he's doing Rishikesh, I know you have found a teammate, but you have not given any proposal, correct? Is he there?
Yeah, I mean, we're not exactly
Why don't you pay attention? Maybe not this program invariance may not be suitable for you because it requires thing, but nonetheless, think about what Hitat and Madhukar said. We can discuss.
Yeah, sorry about the typo. I fixed it. Yeah. So x gets incremented by 1 and y gets incremented by x actually. Yeah. So anyway, and then at the end of the loop, you want to assert that, whenever you exit out of the loop, you want to assert that y is greater than or equal to 0. So now if you know, so of course, I'm not going to get into the details of what are inductive invariants and, what are not, but at least if you know what are inductive, of course, if you're interested, if you want to take this up, we can discuss what are inductive invariants and how you can check them. Okay, and very briefly, inductive invariants are
notes that you can read to quickly get this thing.
Correct, and it's not very difficult. These have some simple conditions and these are easily checkable. For instance, an inductive invariant is one which is true in the beginning, and if you assume that they are true in the beginning of any loop iteration, then they continue to be true after the loop iteration. Okay, so this is like induction. I mean, this is quite like induction in the usual mathematical induction that you know. But anyway, we can get into the details of it. But the point is that, if you think about this program and if you think about some candidates for invariants, then these candidates can be classified as bad, good, or perfect. And the way I have classified them is a bad candidate is one which is not even inductive. For instance, y is greater than 0 is a bad candidate here. It's not even inductive.
Why is it? Oh. Sorry, I missed it.
It's not inductive because, if you, I'm sorry. So first of all, there's one more typo, assume all greater than equal to 0 to be, assume all greater than 0 to be greater than equal to 0. Sorry. Yeah. So anyway, so the point is that y is greater than equal to 0 is not inductive. You can convince yourself that it is not. Okay. Because if you know that y is greater than equal to 0 in the beginning of any loop iteration, you don't know that y will continue to be bigger than or equal to 0 at the end of it. Okay, the reason that you don't know this is because x gets added to y and you don't know anything about x. Okay, so if you're not really tracking what x is using another inductive invariant, you're not going to be able to argue that y is greater than equal to 0 is an inductive invariant. Okay, this is of course a brief explanation. You can think about it and you can convince yourself. But the point is that this is a bad candidate. What is a good candidate? A good candidate is x is greater than equal to 0. Why is it a good candidate? Because it is inductive. It may not be sufficient for you to prove the property, but it is certainly inductive. Okay, because if you know that it is, first of all, it is true in the beginning. Once again, the greater than the inequalities are supposed to have an equality component also. The greater thans are greater than equal to. Yeah, sorry about that. I'll fix it before I upload. Okay, yeah. So now if you know that x is greater than equal to, so first of all, you know that x is greater than equal to 0 in the beginning. And then if you know that it is greater than equal to 0, it is only incremented by 1. So it will continue to be greater than or equal to 0. Okay, assume mathematical integers. We are not worried about overflows here. Okay. So this is a good candidate. In the third case, what you have is x greater than equal to 0 and y greater than equal to 0, which is not just inductive. It is also sufficient to prove the property. And therefore, it is a perfect candidate for you in this case. Okay, so given a program and a candidate, it can be classified in these three ways. It can be good, bad, or perfect, right? So you can write a bunch of programs. In fact, okay, I'll talk about that later anyway. So you can write a bunch of programs and you can have a bunch of candidates, and for each program candidate pair, you can classify them as good, bad, or perfect, right? And then you can make a network learn this thing, and then you can ask interesting questions to the network. Okay. So first of all, notice that the training data for this has to be generated manually, but this is not a very difficult task because there are plenty of benchmarks available. For instance, SVComp benchmarks, I'll send the link if needed. You can actually Google it and find that link for SVComp benchmarks. So there are plenty of programs which look like this, which have just one loop and one assert. Okay. And at least you can write variations of that program. For every program, there are multiple candidates that you can write, and you can check whether these are good, bad, or perfect, and you can generate your training data. Okay. Remember that for this to in order to be able to give this, you need to transform your program into a real input vector of some size, and similarly the invariant expressions or the candidate expressions have also to be transformed. So there are ways to do this. Okay. So some information about this can be found in this paper. So this paper is a very interesting paper. If you're, for general interest, you may read this, but you're not supposed to for this work. But at least from this paper, you can find out what sort of an encoding that you can do to the program and the property so that it looks like a, like a fixed size real, a vector of real values. Okay. So that becomes your program invariant, and now your classification certainly is good, bad, or perfect, which can be, which can be expressed using 3 bits, like how you're doing it in the assignment right now. Okay. And then once you do that, then you can make a network learn whether something is good or bad or perfect. And then you can ask Z3 to synthesize invariants for programs or programs for invariants. You can ask such interesting questions where you partially write a program, leave some holes such that some simple invariant turns out to be a good invariant for it, or some simple invariant turns out to be a bad invariant for it. So there are many things that you can do. Okay, so this is one of the ideas that we had. Okay, so this is related to program correctness using inductive invariants. Okay. Of course, so the entire task is to generate the training data, train a network, and then finally to be able to check properties of this kind. At every step, there is a lot of help available from existing benchmarks and existing work which has been done to transform them into vectors of fixed size. Okay. The other thing, of course, as some of us have looked at the assignment too. So there, you can look at combinatorial games, and you can try and then ask questions about moves in that game. So essentially, what we are doing is so you can classify some move to have certain properties. For instance, if you take a look at this game, this one is called Cinderella and the Wicked Stepmother. Okay. So what is this game? The game is nothing. So there are 5 empty buckets that are kept on 5 edges of a regular of a regular pentagon. Okay, and so the point is that and there are 2 players playing this game, Cinderella and her wicked stepmother. Okay, and this is how it proceeds. Okay, so they say that at the beginning of every round, the stepmother takes 1 liter of water from a nearby river and distributes it arbitrarily over those 5 buckets. Okay, and then Cinderella chooses a pair of neighboring buckets. So Cinderella must choose 2 buckets that are adjacent to each other. So Cinderella chooses a pair of neighboring buckets and empties them into the river. So she empties both of them and puts them back, of course, in their place. Okay, the stepmother's goal is to make one of these buckets overflow. Cinderella's goal, of course, is to prevent that from happening. Okay. And this game is an interesting game, for different bucket sizes. Cinderella has a winning strategy, or for some bucket sizes, Cinderella does not have a winning strategy. So you can learn about this game from the literature. It's an interesting game to look at.
This was an IMO shortlist problem, right?
Yeah, I don't know. I know of this as a game for which people have tried to synthesize strategies.
Yeah, I think I have seen this in some shortlist.
Correct. Yeah, it may be. In fact, there are many games, which have appeared as, there was I also came across, a few other things which appeared in German Mathematical Olympiad or something, where, you have a vector of some 2n size and you are trying to populate it by some numbers from 0 to 6. And there are 2 players playing this number. One player's aim is to make that final number divisible by 9 and so on. So basically the point that I'm trying to make is that there are these interesting games which can be for which you can try and think of a winning strategy. And even if you're not able to think of a winning strategy all the way till the end, you can try and find out what is a good move. So for instance, in this case, given a configuration of buckets, you can classify the choices of. So Cinderella has some choices, right? So namely, she has these choices, that which 2 consecutive ones she chooses. Okay. So Cinderella has choices, and for each choice, you can classify the choice as whether it is good for 2 rounds or not. And what do I mean by good for 2 rounds? So a choice is good for 2 rounds if you know that, if Cinderella makes this choice, she would not lose for at least 2 moves, irrespective of what the stepmother does or what she herself does in the next move. Okay. So we can call such a thing as good for 2 rounds. Of course, this is just a property that I thought of. I mean, it need not be good for 2 rounds. You can make it good for k rounds, or you can think of a different property. The point is that you can classify each configuration, Cinderella's choice as good or bad for whatever it is, good or bad. Okay. And then you can ask interesting questions. Then of course, then you can train a network to learn what is good and bad for Cinderella. And then you can ask Z3 interesting questions for, you can make Z3 ask interesting questions from this network. For instance, you can ask this question that is it possible for Cinderella to lose in 5 rounds if she plays at least 3 moves in those 5 rounds, which were good for 2 rounds. So is it possible? So you can make interesting questions, and you can really ask deep questions and try to see if the network can propose a configuration and a sequence of moves from where even if Cinderella chooses this good for 2 round moves in at least 3 of them, she still loses, right? So you can do some such thing. Of course, you don't have to be limited to, I mean, there is a fair bit of flexibility. It does not have to be this property. It does not have to be, to the extent possible, it may not even have to be this game. But the point is that the game has to be interesting enough such that, there are things that we can do with it. It should not be a very simple game, which is, for which there is a clear winning strategy and there are hardly any training data and there are not even many interesting properties to check. So if a game is sufficiently involved and interesting so that, the winning strategy is not very easily expressible, at least then we can try and find out what is good for 1 move or 2 moves, or, some partially good configurations and partially good choices, so that you can generate a lot of training data and ask certain interesting questions like this. Okay, so this is what I had in mind, and these are, once again, both these things are just indicative of of how broad you can think, and in that then you can define what exactly will be the game, what exactly will be the moves, or what exactly will be the kind of programs, what will be the invariants, what will be the operators. You can fix that. I look at candidate invariants which are only which only have at most 2 operators and 3 variables and 2 constants or something. Okay, so you can fix these things so that you can generate interesting combinations, and then you can train a network to learn some of these things. And that's all that I have.
Madhukar, one question/comment I had about the program invariants.
Yeah.
See, the program invariants, they are, given a candidate invariant, you can easily check what is there to learn about this thing. I mean, it is not.
May I ask if you are giving any more ideas? I have to leave for some reason.
Okay.
Okay, yeah, no, we are not going to give any more ideas right now, but yeah.
I think I will also not ask questions. Okay, so I'll hold my question.
Yeah.
Unless others want to have questions.
Yeah, so you can, if you want to discuss some of these further, we can discuss this with you. You can take this example and then you can try and modify it and transform it to something that's possible, doable, and of course, we think that these things are.
Telling any more ideas, right?
We are not going to tell any more ideas that I told up front.
I want to leave. Okay. So
yeah, please
okay.
Feel free. Yeah.
Yes.
Okay, thanks, sir.
Yeah, so this is what we had. This is just to tell you that you can really think as broad as you want. No matter what domain we are choosing, we should be able to carve out an interesting enough problem if we put in enough thoughts. That's the kind of idea that we wanted to give Hitarth, and I wanted to say that you can really pick anything that's doable by learning, and then we can try and ask interesting questions. And yeah, sir. So would you want to ask what you were?
No, that's all. See, the one question I had with this program invariance is you're not generating the invariance, because the checking whether it's bad, good, or perfect, it can strictly be done just using.
Correct, but you can kind of generate the invariants also. So you can. So suppose you have. So suppose the invariant is basically. So let's say So your invariants, let's say, are of the form variable is less than equal to some constant. Okay, and you have some 5 variables and some 10 constants in your grammar, let's say. So you don't know whether which variable less than which constant is the invariant. So then you can ask this thing that, does there exist you can ask Z3, does there exist a choice of variable and a constant?
Yeah, so the interesting thing will be if this is designed as a way that you can generate potential invariants and then classify. Right?
Correct. Yeah. Or you can also generate variants of the program for which. So for instance, if you know that, this is going to be the invariant, you can leave some holes in the program and let Z3 plug these holes in the program so that the invariant is the invariant for that program.
Right. Yeah. Yeah, I'm going to end the formally, okay, the class session. Okay. So people who may want to, Kapil is still here or no? He left. I guess it is Argadeep who will stick around. Is it? Somebody had asked for discussion.
Yeah, I wanted to talk about my idea.
So you can stick around. The rest can leave. Now the only if Sahil and Zubin are still around, you can either think about this programming invariance thing, or we can talk to you. You have to set up some time to discuss your idea. Okay.
So this is Diganto. I wanted to discuss, do some further discussions with you as well. Like, is there any time that you can specify today or?
Yeah. Okay.
Or, I mean, if not, then I guess we'll wait.
No, let's do that. So since I'll stop recording here.